Nuclear electrostatics, electrical generation through alpha decay. A Van de Graaff generator consists of a hollow metal sphere with a belt passed into it, feeding over a roller. As the belt moves over the roller, it creates an electric charge, which accumulates on the sphere. This can then be discharged. A simple Van de Graaff generator can produce over 100,000 volts. The idea of electricity generation through radioactive decay works on a similar principle. A radioactive source is placed within a hollow metal sphere, and as particles are released, a charge collects on the sphere. This can then be discharged and utilized. For this video study of the concept, I use uranium-238, however a different radiation source could be found. Uranium-238 is a good radiation source for this, as it does not experience temperature increase due to radioactive decay, and unlike most other radioactive elements, can be handled by people in relative safety. The calculations involved are quite simple, and there are no overly complicated formulas to go through. Uranium decay splits one atom of uranium-238 into one thorium-234 atom and one alpha particle, which is basically a helium-4 particle with a charge of 2-. 1 mole of uranium-238 releases 3 million alpha particles per second, 180 million per minute, 10,800,000,000 per hour, etc. Each alpha particle has a charge of 2-, so 1 mole of uranium-238 releases 360 million electrons worth of charge, or negative 360 million elementary charge. What's the point? Well, this is equal to 5.7672 times 10 to the power of minus 11 coulombs. At this rate, 1 mole of uranium-238 would take just over 280,000 years to charge a smartphone. Obviously, direct power draw is not an optimal application for this technology. A much better use of electricity generation through radioactive decay would be an emerging technology, single electron transistors. These use 1 electron to send a single instruction, and this would amount to 6 million instructions per second, MIPS, per mole of U-238. This is a computing speed comparable to late 80s technology, so anything requiring high processing speed also would not work. What would be a perfect application of nuclear electrostatics is, coupled with single electron transistors, electronics which do not require high speeds. A very good example would be digital seismometers, which only record data, and do so less than 6 million times per second, or, even better, instruments on satellites or unmanned landers. Something which would record data over years, if not decades, basically very low-draw electronics, would work perfectly when powered with a small uranium electrostatic generator. This has the added advantage of being much safer than radioisotope thermoelectric generators, which use plutonium-238 decay to create electricity through heat, currently used on unmanned spacecraft. Plutonium is extremely dangerous compared to uranium-238 and much harder to control. At this point, you might be asking, why even bother with all this? Well, generation of electricity through alpha radiation is very safe. Alpha particles cannot penetrate a piece of paper, let alone a metal sphere, so they pose no danger to humans, and there is no chance of radioactive waste release or accidental criticality like in a nuclear power station. It is also 100% green, as people say, producing no waste except for thorium-234, which is produced so slowly that it doesn't count. Humanity would have left Earth or gone extinct in 4.47 billion years, the time it takes for 50% of the mass to be converted to thorium-234. While there is not currently an abundance of possible applications for this technology, in the future electrostatic generators containing 1 or 2 moles of uranium-238 could be embedded within low-draw electronics, powering single electron transistors for tens, hundreds, thousands, millions, even billions of years, enabling humanity to send probes deep into space or onto planets relatively cheaply and extremely reliably.